A miracle compound discovered in a lab is only effective if it reaches its target intact. Delivering a drug through the hostile environment of the human body is often more difficult than discovering the drug itself. Many active ingredients are highly unstable in their raw form. They can evaporate in storage, react with the atmosphere, or face immediate destruction from stomach acids long before they reach the bloodstream. Poor delivery leads to significant complications. A patient might experience severe gastric irritation, or a potent drug could release its entire concentration into the system at once, creating a toxic spike instead of a steady therapeutic dose. Without a way to shield these chemicals during transit, a promising medical breakthrough remains a liability rather than a treatment. Engineers solve this through microencapsulation. This process involves wrapping tiny particles or droplets of an active ingredient inside a continuous, protective polymeric film. The engineering happens at an extreme scale. These capsules typically measure between 1 micrometer and 1,000 micrometers in diameter, often comparable to or smaller than the width of a human hair. This cross-section shows the underlying anatomy. The active ingredient serves as the core, isolated from the outside world by a protective outer shell or coating. This microscopic packaging changes the physical properties of the payload, allowing engineers to turn reactive liquids into stable, dry solids that can be easily handled and shipped. These shells are not one size fits all. Engineers customize the internal geometry of the capsule to dictate exactly how the medicine is stored and released. There are two primary architectural designs. On the right, the reservoir system, or microcapsule, and on the left, the matrix system, often referred to as a microsphere. In the reservoir system, a central core is completely enclosed by a uniform shell. The matrix system is different. Here, solid particles of the active agent are dispersed throughout the entire body of the polymer matrix, like raisins in a loaf of bread. The performance of these structures depends on the polymer recipe. Engineers select inert materials that form flexible, non-hygroscopic films, ensuring the drug remains stable without reacting with its own packaging. By matching the physical geometry with the right polymer, the capsule provides a tailored environment that protects the payload from its specific external surroundings. Effective encapsulation requires a paradox. The shell must be strong enough to protect the drug, but engineered to break apart on command. We can program these shells to open through mechanical or thermal triggers. Some rupture under physical pressure or shear stress, while others remain intact until they reach a precise melting point. Environmental triggers offer even more control. Specialized enteric coatings are designed to pass through the high acidity of the stomach and only dissolve when they hit the specific